Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from the Department of Physics and Astrophysics, University of Delhi. Today we are going to talk on module Radiation Detectors Part 4 under the paper Nuclear and Particle Physics. After completing this module, the students will be able to number 1. Understand interaction of gamma ray photons with matter via Compton scattering. They will also be understanding the interaction of gamma ray photons with matter via pair production, and they will understand the interaction of neutrons with matter. Gamma rays, X-ray photons in matter, Compton effect. In this slide, basically the gamma rays interaction with matter is discussed in the context of Compton effect. We know that when the gamma rays interact with matter, they interact with matter with three different processes: the photoelectric effect, the Compton effect, and pair production. In this slide, the Compton effect kind of interaction is given. Scattering between gamma ray photon with free electron of the absorber. This is what happens in Compton effect. In the Compton effect, the photon, incoming photon, which is nothing but a wave, the photon interacts with the free electron. Free electron means the outermost orbit electron of the atom. And then photon gets scattered and the electrons get recoiled. Now, due to scattering, the photon moves with modified energy because it exchanges momentum as well as energy with the electron. Then the distribution of momentum and energy takes place between the incoming photon and the recoiling electron. So in this case, we find that energy of the scattered photon gets modified and is given by h nu dash is equal to h nu upon 1 plus h nu by m0 c square 1 minus cos theta, where theta is the angle at which the scattered photon is emitted. Energy of emitted electron can also be calculated using the formula EE is equal to h nu m0 c square 1 minus cos theta upon 1 plus m0 c square 1 minus cos theta. Gamma ray, X-ray in matter, Compton effect. In this slide, basically we are going to study more details of Compton effect of gamma ray photon. So as we have seen that gamma ray interact with matter via three different processes: photoelectric effect, Compton effect, and pair production. So here more details of Compton effect are discussed. Now the angle relationship is cot phi is equal to 1 plus m0 c square upon h nu into tan theta. Energy sharing between electron and photon depends on the scattering angle. For maximum electron energy, theta is equal to 180 degree and phi is equal to 0 degree. What is theta and what is phi? We have seen in the previous slide that theta is the angle of scattered photon and phi is the angle of the scattered electron, recoiling electron. So for maximum electron energy, that is for maximum recoil, the photon has to basically scatter at an angle of 180 degree or should be reflected back, and in this situation phi is equal to 0. If we put these two values in the above equation, we can get the conditions for maximum energy transfer to the electron. Even in the extreme case, some energy is still retained by the photon. Since all scattering angles are possible, so we get EE is equal to 0 minus h nu. So what does this mean? This means that when the photons enter in the material medium, they basically have interaction with the electron, and due to that interaction the scattering of electron take place and photon is also scattered. So the energy, if we watchfully see the energy of the recoiling electron, then we get all sort of energy of recoiling electron depending upon the angle at which the photon is scattered. The probability of Compton scattering depends on the number of electrons present in the material, so increases with Z. What does this mean? This means that if we have different material and the same energy photon interact with them, then the Compton scattering will be highest in the material which has got highest Z. So the probability of Compton scattering is basically proportional to Z. You can see gamma ray, X-ray, photon in matter, Compton effect. So we continue our discussion about the Compton effect. Here in this slide, basically we will see how the angular distribution of Compton electron can be estimated by using Klein-Nishina formula. So there is a well developed theory of Compton effect of photons in matter, and that theory was basically developed by Klein-Nishina, and they came up with a formula which gives the angular distribution of Compton electrons, and the formula is shown here, that is angular distribution d sigma over d omega at a particular angle theta, scattering of photon, is equal to 1 by 2 r e square bracket e gamma dash over e gamma square bracket e gamma over e gamma dash plus e gamma dash over e gamma minus sin square theta, and the unit of this is centimeter square per steradian, where E gamma is the energy of the incoming photon, E gamma dash is the energy of the scattered photon, theta is the angle of scattering of photon with respect to the initial direction of motion. D sigma over d theta is equal to 1 by 2 r e square bracket 1 upon 1 plus alpha 1 minus cos theta whole square into bracket 1 plus cos square theta plus alpha square 1 minus cos theta whole square upon 1 plus alpha 1 minus cos theta, and the unit of this is also centimeter square per steradian, where alpha is equal to E gamma upon m0 c square and Re is equal to classical electron radius, and that is basically given as equivalent to 2.82 into 10 to the power minus 13 centimeter. Gamma ray, X-ray, photon in matter, Compton effect. So we continue with our discussion about the Compton effect, that when the gamma ray photon enters in the medium, it interacts with the electrons of the medium via Compton effect. In the Compton effect, we have understood that it's an interaction of the incoming photon, which is a wave or a radiation, with the electron of the medium. Which electron? The outermost orbit electron of the atom, which we are calling as the free electron. So it's an interaction between the photon and the outermost orbit electron. Due to this interaction, the momentum and energy exchange take place between the photon and the electron, and as a result, photon is emitted and electron gets recoiled at some angle. In this slide, basically, the angular distribution pattern of scattered photon is given as a function of different gamma ray energy photons. So here in this slide, basically a plot is given where in this plot, basically the scattering, the number of photons emitted as a function of a scattering angle is given. So here you can see that there is a strong angle dependence of scattering, and with increase in energy, with increase in scattering angle, you can see that different number of photons are getting collected. The maximum, the behavior of the scattering angle is strongly energy dependent. So we can see that corresponding to different energies of the incoming photon, the number of photons emitted it at a particular angle are basically different. Gamma ray, X-ray, photon in matter, Compton effect. So we continue our discussion about the Compton effect. Here in this slide, basically the Compton scattering as a function of gamma ray energy is basically shown for different sizes of detector. Now in this slide, basically one picture is given in which three different curves are being plotted. First curve is for small crystal, it means for a small size of detector. Second one is for medium crystal means medium size of detector. And third one is for large crystal, that is large size of detector. So here basically it has been shown that when the gamma ray of a given energy enters in these three different kind of detectors, different size of detectors, then what happens? When the incoming gamma radiation enters in the detector of a small size, then we observe 3-4 points in the spectrum. They are marked as A, B, C, D, where A represents the peak when no gamma is scattered. B represent when a scattering of gamma takes place at 180 degree, which is also called the Compton edge. C represents the situation when the scattering of gamma ray photon is at angle less than 180 degree, and D represents the situation which is due to various reasons. So now if we observe the behavior of incoming photon of a given energy in three different sizes of detectors, then we observe that the nature of A, B, C, D portion changes with the size. In the case of small size detector, we don't observe, or you can say that A is basically, which is also termed as the photo peak, is very small in size because detector size is small, because of which all gamma photons do not get trapped inside it and there is less photoelectric effect. But as a function of increase in size of the detector, we can say that the gamma ray photon probability of interaction becomes more and more, and because of which you can see that in the detector of largest size there is a clear cut nice photo peak of gamma ray. A represents the photo peak which is considerably high in the detector of largest size, whereas A is the smallest in the detector of small crystal. So it means that in case of a small size detector, Compton effect is more as compared to the photoelectric effect, but with the size of the detector we can say that the Compton effect is lesser as compared to the photoelectric effect. Gamma rays, X-ray, photon in matter, pair production. In this slide we are going to study the third interaction mechanism of gamma ray photon with matter, which is pair production. Pair production is nothing but the energy conversion to mass. What happens is, in the pair production, when the gamma ray energy is higher than 1.02 MeV, in that case this energetic gamma ray when passed through the nucleus, then it basically is absorbed in the medium, resulting in two charged particles, one is electron and one is positron. These positron and electrons travel through the medium, and the positron again gets combined to a nearby electron, and then two gamma photons are emitted opposite to each other. So this process is called pair production. So pair production is nothing but the loss of energetic gamma photon in terms of pair of charged particle production. So in this case, basically in this process, a gamma ray photon spontaneously gets converted into an electron positron pair, and the philosophy of this kind of conversion is shown in the picture given below, whereas a photon with energy greater than 1.02 MeV is trying to pass through the medium, and in the field around the nucleus basically it gets converted into, it is completely lost and electron positron pair is emitted. Positron pair on passing through the matter again gets interact with the electron, and 2 gamma photons of energy 0.511 MeV are basically released in opposite direction. Gamma ray photon, X-ray photon in matter, pair production. So we continue our discussion about the pair production of gamma rays in matter. In the pair production process, case of pair production, the process always takes place near nucleus to conserve momentum. So it is seen basically that pair production always takes place in the neighborhood of the nucleus. Why it is so? Because it is so due to conserve momentum. The process has to conserve momentum. Momentum conservation has to follow in this process. To conserve that momentum, basically the process takes place near the nucleus. Also, it has been observed that the pair production is a dominant process for gamma ray photons of energy greater than 1.02 MeV. Why this energy requirement is there? Because in this process, electron positron pair is produced. So energy has to convert mass, and the mass of the rest mass of electron is 0.511 MeV, and positron is the antiparticle of electron. So in total, the energy of the incoming photon has to be greater than 1.02 MeV to create the pair of particles. Also, it has been observed that in case of pair production, the cross section varies with Z square of the absorber and E gamma. Here in this slide on the right hand side, one picture is shown which is basically nothing is a representation of the probability of pair production as a function of photon energy. So here you can see that this basically variation of pair production, probability of pair production as a function of energy is shown for different elements. So here in this case we can say that in case of lead and aluminum, for low energy photons the Compton effect is dominant, whereas pair production is less. But as the gamma ray energy goes beyond 50 MeV, in that case the pair production basically dominates, and for gamma ray photon of energy around 500 MeV or more, we can see that for all elements, for all observing media, the pair production is the only way by which the high energy photons lose their energy in the medium. Gamma ray, X-ray photon in matter. So we continue our discussion about the interaction of photons with matter. Here in this slide, we can see that all the three processes, the gamma ray basically interact with matter and get detected. The total cross section per atom for gamma ray photon can be represented as sigma is equal to tau of photon plus Z into sigma c plus k pair. So it means the total interaction cross section of gamma ray photons with matter is the combination of the interaction of photons via three different processes. Tau photon is the interaction probability of incoming photon via photoelectric effect. Z is the atomic number of the absorbing medium. Sigma c is the interaction cross section of incoming photon via Compton scattering, and k pair is the interaction cross section of incoming photon via pair production. Extra energy sharing means when the incoming photon has energy much greater than that required to produce the electron positron pair, that is 1.02 MeV, then the extra energy of the incoming photon is shared between electron and positron. And how it is shared? It is given by the equation energy of positron is nearly equal to energy of electron is equal to h nu minus 1.022 by 2 MeV. We can clearly see that the positron and electron almost get equal share of energy when the energy of the incoming photon is greater than 1.02 MeV. In this slide on the right hand side, we can see one picture where the probability of three processes of photon interaction in matter is shown as a function of energy of the photon. So here you can see that the three processes are shown: photoelectric effect, Compton effect and pair production, and it is also shown that in which energy regime they are dominant. So, you can see that when gamma ray photon energy is less than around 200 keV or so, photoelectric effect is the dominant process. But as the energy increases, the Compton effect is more probable as compared to photoelectric effect, and as the energy increase beyond 1.02 MeV, we can clearly see that the pair production dominant process. Interaction of neutrons with matter. So, in this slide basically we are going to study that how the neutrons are getting detected in the detector. So, neutrons, as we know that neutrons are like other radiation, they can get detected via some interaction. If they don't interact, they will not get detected. This is the simple philosophy for any kind of radiation. So, in this slide, basically we will study that how neutrons interact with matter. Now, since electrons do not have any charge, so they interact with matter via strong interaction. Now, we know that neutrons are neutral particles, they don't have any charge, so they cannot interact with the electrons of the medium or nucleus of the medium, nucleus of the atoms of the medium via electromagnetic force. Since they are neutral and electromagnetic force acts between two charged objects. So, there is only one possibility by which the neutrons can interact with matter, and that is through the nuclear reaction. So, neutrons basically interact with matter via strong interaction. What happens is when the neutrons interact with the matter via strong interaction, they undergo some kind of reaction, and as a result of that reaction, some charged particles are produced, and those charged particles basically lose their energy in the detector medium, and then they get detected. They get completely absorbed, and through their absorption or their detection, basically we can say that the neutrons have entered and reacted in the matter. So it means conclusively we can say that the neutrons get detected in the detector through the response of the secondary radiation they produce in matter. So main process in this detection of the neutrons is elastic scattering. Elastic scattering means when the neutron is coming, it is interacting with the medium, and then neutrons are getting scattered through elastic scattering. This happens for neutrons which are having energy less than equal to 1 MeV. Other mode of interaction of neutrons in the medium is via inelastic scattering. In the inelastic scattering, what happens is neutron comes, interact with the material, and then neutron basically get scattered with some less energy, and the remaining energy is given to the atom of the medium and it gets excited. So, basically the neutrons within the medium undergo two kinds of reaction: elastic scattering reaction, inelastic inelastic kind of reaction. How do we differentiate that what is the elastic scattering and what is the inelastic scattering? The simple way of looking at them is that in case of elastic scattering, if the neutron is having the elastic scattering in the medium of the detector, then the atoms of the medium will not get excited and will not give any gamma ray photon in de-excitation. But when the neutrons get inelastic scattering in the medium, the atom of the medium is excited and then it de-excites by giving some gamma ray photon. So this happens, the inelastic scattering happens for those neutrons which are having energy E greater than equal to 1 MeV. Third important process by which neutrons get detected in a detector medium is via Radiative neutron capture. Radiative neutron capture means the neutron get absorbed in the medium and then a gamma ray photon is emitted. Like N plus Na plus Za. Za means the material, the atom of the material medium of the detector. The reaction is Za plus 1, that is a new nucleus is formed, Za plus 1 plus gamma ray photon is emitted. This gamma ray photon then interacts in the medium and then it gets detected. Another important reaction that basically gives the identification of neutron is via substitution reaction. Substitution reaction means it may happen that the neutron interact with the material medium and then it is absorbed and a proton is emitted. That is, neutron interacting with the medium releasing out a proton, or a neutron interacting with the medium and a deuteron is released, or a neutron interacting with the medium and alpha particle is emitted, or a neutron interacting with the medium and tritium is emitted. So you can see that in the substitution reaction, the charged particles are emitted. These charged particles lose their energy in the medium, they get completely detected, and with their detection, we can get an idea about the detection of neutrons. Another important mechanism by which the neutrons can get detected in the detector medium or detectors is via fission reaction. Fission reaction means neutrons enter in the detector, they basically initiate some fission reaction. Due to that fission reaction, two heavy charged particles are produced. These charged particles are energetic particles. They lose out their energy in the medium, they get completely detected, and with their detection, basically we can detect the neutrons. This process takes place for neutrons with thermal energies. Interaction of neutrons with matter. Now we have seen that neutrons interact with matter via a number of processes like elastic scattering, inelastic scattering, capture, neutron capture, plus and so on. So total reaction cross section of the neutrons in matter is also sum of interaction due to these individual processes. So total reaction cross section sigma total for neutron in matter is equal to sigma for elastic scattering plus sigma for inelastic scattering plus sigma for capture cross section for capture and so on. In the picture on the right hand side, the plot of this total cross section as a function of neutron energy is shown. Now in this picture, from this picture we can basically draw a few conclusions. First of all, the first conclusion that we can draw is that the cross section decreases with increase in neutron energy. The second conclusion that we can draw, that for low energy neutrons, the behavior of cross section follows the 1 by v rule, where v is the velocity of the incoming neutron. So for low energy neutron, the total cross section is directly proportional to 1 by v. After that, for little high energy neutrons, we can see that resonance phenomena takes place, that is, neutron is absorbed, the nucleus of the medium get excited and then de-excite by releasing energy. So resonance peaks are basically observed. For still high energy neutrons, which are termed as the fast neutrons, we can say that the total cross section decreases. So students, let us now summarize what we have learnt in this module. There are various concepts, various things which were discussed in this module. Now it's time for us to recap what we have learned so far. The first thing that we learned is that Compton scattering is an effective way of losing energy for gamma ray photons. Another important thing that we learned in this module is that Compton scattering is the most important interaction mechanism for gamma ray photons with energy E gamma greater than 400 keV and for materials with high Z. Third important thing that we learned in this module is that for very high energy photons, that is E gamma greater than 40 MeV, interaction with matter is only through pair production. And there is one more thing which we have learned in this module is that neutrons interact with matter via a variety of processes and get detected by the detection of secondary radiations produced in these processes. Thank you very much.